Dear friends, I welcome you all for the new episode. I coined the term E5 series of lecture. The term E5 refers to environment, energy, economy, engineering, and education, which are considered to be the 5 pillars of sustainable research and technology development. I believe we'll have lectures from various experts across the globe on either one of this topic or combinations of. Today, we have a wonderful speaker, Dr. Gururaj, an internationally renowned recognized researcher with work focused on electrochemical sensing and quantum chemistry. Currently, he is working as a professor at Nite Meenakshi Institute of Technology, Bangalore. Before starting his lecture, let me start a few words. Nanotechnology meets chemistry and theory meets real world impact. What happens when we zoom into the invisible world of electrons dancing on the carbon surface? In this lecture, he will unravel how we can understand electron transfer using voltammetry and density functional theory. I would say a fusion of deep theory with experimental evidence. So, get ready to enter into the world where chemistry becomes code and electrodes tell stories.
Hello everyone, I am Dr. Gururaj Kudur Jayaprakash, currently working as an assistant professor at the Department of Chemistry, Nite Meenakshi Institute of Technology, Bangalore. Today I am going to give a very short talk on understanding electron transfer process at carbon electrodes through voltammetry and density functional theory. In this talk, what we will discuss how we can use voltammetry and density functional theory to understand how electron transfer process at the carbon electrode interface. In this talk, we will first we will discuss short introduction about the voltammetric methods, and then we will discuss about the carbon-based electrodes. At the end, we will discuss some of the important concepts of the density functional theory to understand the electron transfer process. Later, we will discuss methodology like how we can perform both experimental and theoretical part of the these kind of work. In the results section, first we will discuss defected graphene systems, doped graphene systems, mainly hexagonal boron nitride graphene system, and then we will discuss about how both theory and experiment can be matched, or how we can gel voltammetry with the in particularly with the conceptual density functional theory parameters. So first we will discuss at the time cytosine and adenine functionalized graphene system, and then at the end surfactant modified graphene system we will see. So let us start this talk with the introduction about the cyclic voltammetry. So before thinking about the cyclic voltammetry, we need to remember two important scientists. One is Professor Jaroslav Herwasky. He's from Europe. And then we need to think about the Professor R.S. Nicholson. In early 1900s, Professor Herwasky developed the polarographic method. For this method, he got Nobel Award, which itself says how important was this method at that time. So we can use polarography mainly to uh, detect the metal ion concentration. So in the later part, what happens in 1940s and 1950s, there was a rapid development in the spectroscopic method. Due to it, people or research scientists were not that much using polarographic method. So slowly again, electrochemical methods came to limelight because of the contribution of Professor R.S. Nicholson. Mainly, Professor Richard S. Nicholson has developed the mathematical equation how we can calculate the electron transfer kinetics at the electrode surface using polarographical methods and cyclic voltammetric methods. So he has Professor R.S. Nicholson has published series of papers like how we can understand the electron transfer process at the electrode interface. First, he published paper in Analytical Chemistry in 1964. Then he published series of papers. Like in particular, his main aim was to uh, calculate the electron transfer kinetics and redox reaction mechanism using the cyclic voltammetry. All these things gave birth to the concept called cyclic voltammetry. So, what is cyclic voltammetry? If we think about cyclic voltammetry, we have few important words here: cyclic, volt, amp, metry. Metry means measurement, amp current, volt voltage, cyclic is a another term. So, as name only says, in voltammetry, metry, as I told just now, metry means measurement. So, what we are measuring here? We are measuring potential and the current simultaneously. As like this will give the typical voltammogram. Here, what happens in the cyclic voltammetry? We will we will start the cyclic voltammogram from the initial potential, initial to final we will reach. Once after reaching the final potential, again we will sweep the potential back to the initial. So what happens here? We have gone from initial to final and then returned to where we have started the potential. That is nothing but the initial potential. These process occurs like in a cyclic manner. Therefore, this method is known as a cyclic voltammetry, and respective plotting of the current versus potential curve, we can call it as a cyclic voltammogram. So here we can see a very typical cyclic voltammogram. So here what we have done, we have sweep the potential from negative to positive. So here this is nothing but the initial potential, this is the final potential, and again we come back to the initial potential. Here we can see when we sweep the potential towards the positive direction, what we can observe, we can see the anodic peak current, and this is nothing but the anodic peak current, and this is the anodic peak potential. So when we reverse the sweep, what happens? We can see the cathodic peak current and cathodic peak potential. So this is a typical cyclic voltammogram. How we can perform this cyclic voltammogram? So to perform this cyclic voltammogram, we need three electrodes. If you think about any electrochemical experiment, a common man or a common student can think we need two electrodes, right? Because we need they just think about we need an anode and the cathode. But what is difference in the voltammetry? Why we have to use the three electrodes? Because here we are measuring two important parameter, like when potential changes, how the current will vary. Since we need two important parameters here, between working and the reference electrode, what we can measure the potential. Why? We need some standard to compare the potential. That's why we need a reference electrode. So between working and reference, we can measure the potential, and between working and the counter electrode, what we can measure? We can measure the current. So to perform cyclic voltammetry, if we should, it will be good to have the three electrode system. So now let us start to think it in a molecular level. So why? Because when we perform the cyclic voltammetric experiment, though all the three electrodes are important, very important for us is the working electrode surface. Let us think it in a molecular level, how the, how the electron transfer can occur at this level. So let us think about we have some carbon electrode here. So imagine this one as some typical carbon electrode connected to a potentiostat. So when we apply the potential, if the potential is or we can think like the if the electron level of the working electrode is below that energy level, below the HOMO of the analyte, when we apply the potential, what happens? The energy levels or the electrons energy levels of the HOMO of the electrode, or if we think about working electrodes surface where at the electrons at the highest orbits, if we think about the molecular level, and if the students are from the solid state chemistry background, they can think it as even as a valence band and the conduction band. So this is just I'm explaining in a molecular level quantum mechanics. So imagine like a carbon surface as a some big molecule. If I think about a big molecule, it has a HOMO and the LUMO. So here what happens at the beginning, the HOMO energy level of the electrode is lower than the HOMO of the analyte. So when I'm applying the potential, what happens? The energy levels of the electrons keep on increasing. At certain point, what happens? The energy level of the uh, HOMO of the electrodes will be higher than the HOMO of the analyte. That time, what happens? The electron can hop from um, HOMO of the electrode to LUMO of the analyte. This is nothing but oxidation of the electrode. That means loss of electron in the electrode surface and reduction of the analyte. That means analyte is gaining the electron. Let us think of what happens, as I just now told, we are using a term cycle. That means I am sweeping the potential in a reverse direction once after reaching the um, final potential value. At that time, what happens? The HOMO of the analyte will be higher, so that it can jump now the electron can jump from the analyte to the electrode. It is nothing but oxidation of the analyte and reduction of the electrode. So this is a typical molecular view. Now, to perform this experiment, mainly we are using the carbon-based electrodes as the working electrode. So let us start to see or discuss about the carbon-based electrode. So as I have told at the beginning, when Professor Herwosky developed the polarographic method, he was using the uh, dropping mercury as a working electrode. So, that may be fine during the early 19th century. Then in 1940s, 50s, or even in 60s, people started to, refuse to use mercury. Why? Because it is very toxic. So, what Professor Rolf Norman Adams, or is commonly known as Professor R.N. Adams, what he did, okay, let me think some alternative. What he done, he made some carbon suspension, and he started to use like a instead of dropping mercury, he started to use the dropping carbon. So slowly he understand or slowly he modified the methodology, and he developed a new type of electrode system that is nothing but carbon paste electrode. So why this carbon paste electrode is very common? Because if I think about the carbon paste electrode, it has comparatively low resistance and it is very cost effective. So how, as name only suggests, carbon paste, that means we will take some carbon powder, typically graphite, or even one can consider a graphene, carbon nanotubes, or any conducting or any semiconductor form of the carbon. So if I just think about graphite also, it is comparatively very cheaper. And one more big advantage is if we think about the carbon system, it is possible to miniaturize it. For example, students or the researchers already know about possibility of the miniaturization of the carbon electrodes, in particular carbon fiber. So already widely known, these carbon fibers, even we can insert it on a mice or some living animal's brain, and with that we can measure the concentration of the important biomolecules or neurotransmitters like a dopamine. So one of the major advantage of the another major advantage of the carbon based electrode is you can renew the surface very faster, and it is very easy to modify them, and it will give comparatively low background current. So though it has so many advantages, it has some disadvantage. If you think about the kinetics, electron transfer kinetics of the carbon electrode system, when compared to the metallic electrodes, their electron transfer kinetics is quite low. How we can improve it? We can improve it by adding the catalyst. If we add some catalyst to carbon electrode surface, what happens? It will improve the kinetics. As a result, sensitivity will be increased. Sometimes nanoparticle or some catalyst will increase the stability of the electrodes. Another major advantage here is when catalyst present on the carbon-based electrode surface, what happens? They will mediate the electron transfer between the working electrode and the analyte. So now comes the term called quantum chemistry. How we can use quantum chemistry to understand the electron transfer process at the electrode? Yes, because when we model the, if we model the electrodes interface, we can easily predict the electron transfer properties. In particular, where the oxidation of electrode will occur or reduction of electrode will occur. So one of the main advantage or the role of quantum chemistry here is, even if we go for higher methods, higher end methods like HRTM or scanning electron microscopy, we can know the surface in a atomic scale level, but we cannot know where the electron transfer process is occurring. In particular, where the which sides of the electrodes may be prone for the oxidation, which sides of the electrode is prone for the reduction. These things will be very difficult. Even if we can measure it in a microscopic methods, they will be very costlier. Therefore, we can use quantum chemistry here. So now we will just think like how I can prepare the carbon-based electrode. So to prepare the carbon-based electrode, it is very simple. You take some carbon powder. We will, in our case, we will take graphite, and we will add some binder. Here the silicon oil is the binder. You just add it to the pestle and mortar and grind it for 20 to 40 minutes. Then you will get a homogeneous paste of the carbon and the binder, or the graphite powder and silicon oil. Then just take it and fill it in a Teflon tube. So this Teflon tube will be connected from a copper wire behind. Why? To for applying potential from the potentiostat. So fill it. When you fill this, it looks like this. The surface will be not that much homogeneous. So what we can do, you just take some, like butter paper or smoothen paper, and do it, smooth it on its surface. It then you will get like a, polishing mirror like that image. At that time, electrode surface look like this. Okay. So now let us think it in a molecular level. So even I have told we are using the graphite powder. So we know graphite is made from the, many layers of the graphene. So as we know, when I dip the electrode to analyte solution, what happens? Most of the reaction will occur at the first layer of the graphite layer. So that is nothing but graphene. In terms of, I'm not saying graphene in terms of the experiments for and graphene experimental or experimental importance or experiments. I'm saying if I think in a molecular level, at the first layer of the graphite, maximum electron transfer is occurring. So that is nothing but the graphene layer, but it is different from the pure graphene. I'm saying to just for the modeling constraint, because we cannot mimic the experiments in the theory, or we cannot make experiment as per the theory. We need to come in between. So this is some kind of assumption. The at the first layer, maximum electron transfer will occur. Then what we have done, we have added some binder. Why binder is important? Because if I put only carbon powders, there will be, they may fall into the uh, a- analyte or to the electrolyte. So what we have done, we have added some binder. So if you think about the silicon oil is not that much conductive. Imagine like this is some upper surface of the graphite paste electrode, and there are some spills of the silicon oil. Why we need to consider? Imagine this is a semiconductor. This one is reacting. In addition to it, I have some binder. They are not that much good conductor of the electricity. So what happens here, like electron transfer won't likely to occur here, right? Because it's a not that much good conductor. So the electron transfer may occur at this portion. So now how we can modify the electrode? One of the easiest method to modify the electrode is add catalyst during the preparation only. Here I have some carbon powder, binder. In addition to the carbon powder and the binder, I have added the catalyst. What then I follow the same procedure. I grinded it in a pestle and mortar for 20 to 40 minutes, and then I paste it and polish it on the smoother paper. Now, how the surface may look. Here this one we done this work with the iron nanoparticle. Here what happens? Here we can clearly see like some nanoparticles are present at the surface in addition to the graphite powder and the silicon oil spills. Now we can think, as we know, nanomaterials have a higher surface area. Now the electron transfer process may occur at the graphite powder and at the nanoparticles. Since nanoparticles are highly reactive and they have a higher surface area, there is a maximum probability that the electron transfer process will be mediated from these nanoparticles which are present at the graphite powder, at the upper layer of the graphite paste electrodes. So another type of the modification is surfactant immobilization. Here the procedure is same. Once after preparing the working electrode, what we did, we just added a drop of a surfactant on the electrode surface, like a surface immobilization. Then we leave it for some minutes to for the deposition, and then we started to use. If we prepare electrode like this, what happens? Now I have a you know silicon oil, and then I have a surfactant. This is nothing but surfactant head. Here you can see surfactant head, and this is surfactant type, right? So usually how the surfactant head will be made from some heteroatoms. Some surfactants can be prepared by using pyrimidine, or some other kind of the carbon system with one heteroatoms. It may be usually it will be oxygen, nitrogen, and sulfur, most commonly used in the surfactants. Now we will start to think, like now we have understand experimentally, or we made a assumption at the topmost or the upper surface of the graphite paste electrode, maximum electron transfer will be occurring. Now what we can do, we can use theoretical methods. If I think about theoretical methods, like mainly quantum mechanics based theoretical models, we can use the different set of models. Like one can use density functional theory, Hartree-Fock theory, even Monte Carlo simulation methods. There are so many methods are there, and each methods have its own advantage and disadvantage. We are more interested in density functional theory. In particular, using density functional theory, we are working on conceptual density functional theory parameters to understand both local and global electron transfer properties of the electrode interface. So, if I think if anyone want to interest in the is interested in the density functional theory, what they need to do first, they have to go from the very basics. They should go from the Schrodinger equation, and then how to solve this Schrodinger equation for the multi-electron model, and then they can go read about the Hartree methods, Hartree's approximation, and then they can think like, if we what's the major thing about the density functional theory is we are we are mapping one-to-one relation from the electron density. So density functional theory was mainly using two important research papers from Walter Kohn, Holmberg, and Liju Shang. So the Walter Kohn is the professor, and they are his students. So we can read about the very two important papers of the Walter Kohn in 1964 and 1965, right? So then we need to know another important concept, Foucault functions and the frontier molecular orbital theory. So again, like Kenichi Foucault, probably he's the first Japanese scientist to receive the Nobel Award. So in Asia, he may be top 10 research scientist who received the Nobel Award. Probably after C.V. Raman, he may receive this prestigious award. So Kenichi Foucault, he was an organic. He was basically he's more interested in the uh, quantum mechanics. Uh, in Japan, he found the position for the fuel chemistry, fuel related research. Though he worked like organic concept and or fuel hydrocarbon chemistry like that. At that time, he also started to devote his time to understand the quantum mechanics. So before density functional theory only, he is the one of the prominent scientists. He earlierly he made an assumption electron will always jump or most probably jump from the highest occupied molecular orbital. Electron will most likely to go for the lowest unoccupied molecular orbital. This is the assumption he made. For this assumption and for proving this assumption, he got Nobel Award. Uh, Later in 19, after the development of the density functional theory, Professor R.G. Park, again he is also from the USA, he started to use the conceptual density functional theory parameters for understanding the electron transfer parameter. What Kenichi Fukui was saying, like before the electron transfer process, how the electron will, where the electron can jump or where electron can receive a molecule. That nothing but the homolumo concept. What R.G. Parr developed the functional is after the electron transfer process, where the maximum changes occurring at the electron density in the in a given molecule. So he named his functions as a Foucault function. So though Foucault is not developed it, he developed the homolumo concept. R.G. Park, to respect the pioneering work of the Kenichi Foucault, he named this functional as a Foucault function. So Foucault function can be, we can in a shorthand, we can define Foucault function as shown in this equation. It is nothing but derivative of the electron density with respect to the total number of electron at constant potential. Okay. Here we have two important terms, again plus and minus. Plus is nothing but addition of the electron. That means if I add an electron, uh, how the electron density cloud around a molecule will change. I will know. Again, minus means if I remove the electron, how the electron density cloud is changing. So this is Foucault function. How we can understand with some kind of analogy very easily. I will explain it in the upcoming slide. So in particular, I am using analytical Foucault function based on the auxiliary density perturbation theory. Again, this method was developed by Professor Roberto Flores Moreno. He is a Mexican and he developed this method when he was in USA. Um, so if someone want to know about how we can integrate or how we can compute analytical Foucault function using ADPT method, they need to refer these papers. So now let us try to understand frontier molecular orbital and Foucault function. So here imagine you have some molecule. This is nothing but some small portion of the graphene or some upper portion of the graphite layer. So imagine you give some plain cake to a kid, and you close your eyes, and when you give the plain cake to a kid, obviously you think about he can eat any portion of the cake, right? Because all portion of the cake is even or it looks similar. So there is a maximum possibility that he can eat it any portion of the cake. So this is nothing but frontier molecular orbital. So if I take the you know graphene system, and if I calculate like a homo orbitals, it look like this. So now just flow after some minutes, you may see the plate completely complete cake may be vanished, he may ate it. So that means you basically you don't know which portion he ate it, because all uh, all carbon atoms, if I think about graphene here, all carbon atoms in a same position. So electron can hop from any place, or all places have a equal probability for the electron transfer process. So this is, if I think both Foucault function and frontier molecular orbital, I've you may feel like what's the use of these two methods? Now let us think. Here I have a graphene or a upper portion or the first layer of the graphite surface, and I added some surfactant molecule. Let us imagine it like a cake with a cream. So before giving cake to the kid, you may think like most probably he ate the cream, right? So this is nothing but frontier molecular orbital. That means before eating, you are guessing, before that kid ate the cake, you are guessing where the electron transfer processes occur. Now imagine you close your eyes for 5 minutes and then open it. You may see that a cream portion of the cake has disappeared. That means you think that he ate the cream portion of the cake. So now you can confirm it. He will he ate the cream portion of the plain cake, right? Because before eating, you guess at which portion of the cake he ate it. And after eating also you observe the cake. So, that is both are matching. That's why if frontier molecular orbital and the Foucault function, if they complement to each other, we will know pre and post electron transfer process, so that we can clearly know if I take a electrode system or any molecule where the electron can come from, where electron can go, uh, pre and post process. This is nothing but this image. Now imagine another thing, like I put a chili, cream, and cake, right? So usually you guess, uh, before, no kid, most of the kids won't like to eat chili. You think that okay, he won't eat the chili, and after 5 minutes, you again see that plate, that cream portion has disappeared, right? So this is now again, this is also quite simple to understand. Imagine here I have a typical carbon system. I have boron and the nitrogen. I have two atoms here. So like this is the homo orbitals, like boron and carbons are homo orbitals. And here you can see red region, boron and carbon. That means we will go deeper in the upcoming slides. That means here also you can understand why this analogy is important. Most importantly, now we have some problem. Like imagine I have a plain cake, I have a cherry, I have chili, and I have a cream. Now we don't know where the electron transfer process occurs. In a real system, you think you take some carbon composite, you have a two electron donating group, one electron withdrawing group, and you want to know which electron donating group may transfer the electron, or which electron out of two electron donating group, which one have a most probability to donate the electron. You may it is quite difficult to know. So now if you compute the homo orbitals or the frontier molecular orbitals, you will know before the electron transfer process where the electron transfer up occurs. And now you can see like he by Foucault function after the electron transfer process, again if it is matching with the homo orbital, you can confirm your result much, or you can say very strongly the electron transfer process occur at this region only. So let us start to think how we can do this calculation. So our idea is to use the academically free softwares for this purpose. We are using Synapsys software. Again, it is developed by my advisor, Professor Roberto Flores Moreno. This is all academically free software. By using this builder, a molecular builder Synapsys, we are building a molecule, or we are constructing, or we are modeling we are making atomic scale modeling of the electrode surface, and then we are using Daemon 2K to run the density functional theory based calculations. Again, once after running the calculation, again we are using Synapses to plot them. Nowadays we are running with many functionals, but we most to for the time constraint and for the computational resources constraint. So when we run the calculation, initially we run with the VWN functional with the double zeta VP basis sets at the beginning for the optimization process. If we want to go little deeper into the energy parameters, we will run with the PBE functional with the TZVP basis set. So if you want more accurate methods, if you want to compute more accurate energy values, we may go for the higher functional like P3LYP 6311G star basis set. Again, it depends what kind of the system we are choosing. So, how we can run this calculation? Just you write the geometrical cartesians. Like for example, this is the geometric coordinates cartesians of the water molecule. We give a keyword called optimize. That means it will optimize the molecule. And then we give the basis set. Here, for example, we are selecting the DZVP method. So third line mainly describes the uh, which kind of the Cartesian coordinates we are selecting. Here we are taking the geometric Cartesian, or if some students are interested, they can also select the zeta matrix, z matrix coordination. Uh, Now, again, we can give some more parameters. Like if you want to calculate Foucault, give the term Foucault. If you want to calculate frequency, give term frequency. If you want to calculate molecular orbital, just give MOS. Like that, one can read the manual and he can give the different parameters. Now, once after running this, after preparing the input file, you just have to give this daemon minus op command to run this calculation. For example, here I am taking water molecule. I have given the water dot in. So once after the completion of the calculation, you will get a term called dot out. There you can see the output. For example, this is a optimization of the water molecule. You will see the output file like this. Once after this, you select the optimized structure and give some keyword like print Foucault MOS. It will print the molecular orbitals, and then Foucault, it will compute the Foucault function. So now in the output file, it will look like this. Now in Synapses, how we can, when you open this molecule dot out file in the Synapses, it will look like this at the beginning. And then you will get some, you can go to plot manager. You will see these parameters, then go for the MOS, means molecular orbital, select the highest occupied molecular orbital, just click on it and give some suitable ISO values and grid values. You will get homo orbital. Now, if you want to do the Foucault function, what you have to go? Again, you go back to the plot manager, and at the scalar, you select Foucault left for the Foucault homo orbitals. Okay, you will see like this. Now, let us come back to the graphene system. Like I have given a simple example, water molecule. Now, if we want to go for a realistic models, we need to model the carbon surface. Like if I think about the graphene, we know graphene is has a indefinite or infinite size. So it is by molecular DFT, we cannot model the infinite size. It is very difficult, right? So to know this, what we start to think in 2014-15, we start to think about the graphene system. Like let us select some small portion of the uh, aromatic carbon systems, and then we will see whether any atoms here will resembles to the original graphite or the original graphene atoms. So here we selected C24, C54 and C96 model. So this is nothing but the pristine graphene or a ideal graphene. But in reality, what happens? Graphene has some defects. For example, here you can see like fourth and 10th carbon atom. Sometimes while preparing the graphene, due to the excess of heat, what happens? Some atoms will rotate. For example, here you can see like fourth and 10th carbon atom. Here we are seeing it has rotated 90-degree. As a result, what happens? The four hexagons become two heptagons and two pentagons. Sometimes due to the experimental synthesis methods, the some carbon atoms can be completely misplaced. As a result, what happens? These two hexagons will become one octagon, and these two hexagons become two pentagons. This is nothing but the Stonewall's defect. This is nothing but the double vacancy defect. Now let us think like how we can use this model to understand the graphene electron transfer properties. So now, as we know, if I take about the pure pristine graphene, the carbon-carbon bond length will be 1.42 Armstrong, right? So if I think all the model, we can see at C24, the bond lengths are varying very highly. At C54, the bond length variation is quite low. But if I think about the C96, the bond length variation still very, very slow, and it is almost coming to the nearest to the experimental carbon-carbon bond lengths of the uh, graphene. Then we know, like if I take about the ideal pristine graphene, the carbon charge will be zero. That means carbon atoms won't have any charge. Here you can see at the C96, like it has a carbon-carbon bond length near to the graphene atoms, graphene carbon atoms, and charge also almost zero. Now we can, this suggests that if I take C96 model, the seven hexagon which are present at the core will, you know, mimic the carbon atoms of the graphene system. Then what we did, we plotted the homo orbitals. Here we can see like all carbon atoms of the graphene are present in a are almost same, right? Because each carbon atom's bond length and the charge is same. So electron transfer process, electron can jump from any place, or electron can come. Here you can see LOMO orbital can come to any place. Now we plotted the Foucault function. Here we can see in Foucault function, this is the Foucault colored isodensity plots. Here red color region means F minus means more probable region, are more most affected, are the maximum changes occur at the red colored portion after the removal of the electron or after the acception of the electron. Here you can see all carbon atoms are have an equal probability for electron removal or electron acception. But we know when the defect occurs, what happens. Here you can see uh, homo orbitals are not located at the carbon atoms which were rotated 90 degree, but LUMO is located here. We can think it in something like that. When the two carbon atoms rotate 90 degrees, they will add, the bond length will keep on changing. So here we can see the two carbon atoms which are rotated, their bond length has decreased. That means two nucleus which are very close to each other. Again, it is difficult to remove the electron, because it is very difficult to steal the electron where the two nucleus are very close. Therefore, HOMO is not located here, but LUMO is located here because incoming electron can accommodate here because two nucleus which are close to each other. And then we here we can see the you know Foucault negative. That means after the removal of the electron, here you can see where the maximum changes occurs, and after the electron addition, where the maximum changes occurs. So to make it very clear, this is Foucault colored isoplot. If we want to like just if we plot the Foucault isosurface, here we can see, yeah, clearly um, uh, there is no changes occur at the other portions when compared to this portion, right? But when after the addition of the electron, maximum electron cloud density is changed here. That means if I add an electron, this will come to the if there is a Stonewall's defect, that means the two carbon atoms which are rotated 90 degree, they have a maximum probability to receive the electron and less probability from to remove the electron from those side. Now this is nothing but the double vacancy defects. here you can see like octagons and pentagons. If after the defect formation, electron transfer process is not homogeneous, right? Because electron can at the ideal graphene, electron can be removed from any portion, but after the double vacancy defect, electron can be removed from most probability at certain portion and less probability at certain portion, because again here the planarity will break and carbon-carbon bond length will change. If someone is interested, they can read our JPC article. There we have discussed like why particular carbon atoms have a more probability for the electron removal, more probability for the electron acception based on the earth field charges and carbon-carbon bond length. Now, let us try to, club experimental and theoretical chemistry later. So here we can see this is a typical cyclic voltammogram. BCPE means bare graphite paste electrode. That means here I have only graphite powder and the silicon oil. When I perform the cyclic voltammogram, what happens? We won't see any redox peak. Why? Because the electron transfer again like a typical carbon system, it cannot give. But if in presence of ferrocene, what happens? That we can see clear, both oxidation and reduction peak. What it says that from this diagram, experimentally, I know if I have a ferrocene molecules at the carbon electrode interface, the electron transfer process occurs at the both oxidation and reduction will be mediated by the ferrocene. This work we published in Electrochemical Acta. Now let us try to visualize the ferrocene modified carbon based electrodes in a atomic scale level. Here we can see when I perform the experiment, I don't know how ferrocene may orient on the carbon surface. But if I make a model, I can know. Here you can see like at the different angles, I have placed the ferrocene molecule and then optimize the structure. You can see the lowest probability or the lowest energy is in the at this conformation. So when I perform the experiment, most probably ferrocene may fizzes out on the carbon surface like this. And here I haven't considered the second, third, fourth layer of the graphite because of the computational sources restraint. Then what I have done, I have made the Foucault function analysis. Here you can see this is a carbon system. Here, F minus. If I remove the electron here, electron may go from any places, right? So this one also we published in the these results also we published in the Electrochemical Acta. Why again it is like a plain cake. An electron can be removed from any places. Here what happens, this color will give like blue color regions have a less reactive, red color region is highly reactive. Now if I place ferrocene or analyte on the carbon surface, and if I calculate the Foucault negative, I can clearly see at this system, if I remove a electron, maximum electron density changes occurred here. That means ferrocene, through the ferrocene, oxidation of the electrode is occurring. Now, if I sweep the electrode potential in the reverse direction, again you can see at the bare carbon, all carbon atoms have a equal probability to accept for the electron acception. But now, if I see it in presence of ferrocenium, the electron may jump to the iron portion of the ferrocene. So this what like this way we can understand how the electron transfer mediation occur by the catalyst at the electrode surface. Now again we went for the as I discussed in the while explaining the Foucault function boron co-doped graphene system. Here I have a graphene, as I have told, like these 1, 2, 3, 4, 5, 6, and 7 carbon uh, are the 7 hexagons, looks exactly similar to the graphene. What happens if I dope at the different concentration? We can see. For example, here we can see if I dope with a single HPN hexagonal ring, here you can see these are all the boron. When boron is present, the electron can go out from the boron. But if I think nitrogen, electron may come to the nitrogen. That means homo orbitals are located on the boron and the carbon atoms. That means electron is very easy to remove from the boron and carbon atoms of the graphene when it is doped with the HBN ring. But for the addition of the electron, it will be easy at the nitrogen and the carbon atoms. Why? Because each atoms have a different electronegativity. Now, to make experiments more useful, we have synthesized the graphene, and we modify the graphene surface from the two amino acid amines, cysteine and the adenine. Here you can see this is cysteine and adenine, and then we try to understand how the dopamine electron transfer will occur, and we publish this result in the microchemical journal. So here we can see this is a typical bare carbon-based electron transfer process uh, for the dopamine electron transfer. That means if I have a bare carbon-based electrode, how the dopamine redox reaction occur here. But if I think A is I think A is um, here it means cytosine and adenine, right? 1 minute. Yes, A is cytosine and B is the adenine. So here we can see, like, though I have two different modifiers, from this picture it is very clear that if I add the catalyst, electron transfer process or the maximum electron transfer process occurring between the dopamine and the electrode surface, mainly in presence of the catalyst, right? Why? Because the redox peak currents are high at the catalyst. But in one concept, it is very difficult to understand in an experimental way. I have a two catalysts. Both catalysts are not working in a same range. That means catalyst B have a higher redox current when compared to catalyst A. Why this is occurring? Here we can use the conceptual density functional theory local electron transfer properties. IP is nothing but ionization potential, E electron affinity, W minus electron donating power, W W plus, omega plus and omega minus, electron donating and electron accepting power. Here you can see cytosine have a higher electron donating uh, or electron donating power when compared to the adenine. Omega minus is almost same, right? So this will give the why I'm getting different redox current at the electrode interface. uh, Now we can also use, if I have the two catalyst where the electron transfer may occur. Here you can see the at the cytosine, you can clearly see here nitrogen has more. If this present on the carbon atoms, it is easy to remove the electron from here, and then it is easy to add the electron here. That means the if I think about the catalyst, all portions are not equally probable for the electron removal and electron addition, because each um, we have a many heteroatoms, carbon, nitrogen, uh, and hydrogen, right? All have a won't have a equal electronegativity or equal electron transfer abilities, right? Now here we can see Same for the cytosine also. Here again, HOMO is matching with the F minus, LUMO is matching with the F plus. That means if the adenine present at the electrode surface, the nitrogen atoms of the adenine have the most probably donate the electron, and carbon atoms of the adenine most probably accept the electron. We have discussed like some grinding modification. That means there in the earlier works, I have showed like what happens if I grind the ferrocene in with the carbon paste, how the electron transfer process occurs. If I grind the two different catalysts, how the electron transfer process may vary, how both experimental and theoretical parameters may overlap with each other. Now we will think like surfactant immobilization. What here we are doing, we are adding some surfactant on the electrode surface just by just take some micropipette and add certain like 1 to 10 microliters of the surfactants at the on the electrode surface, and then you dry it and start to use it. Well, if I make the experiment, it is very difficult again to see like how the surfactant may be preserved on the carbon surface. Like i- to make model what we assume, imagine uh, the phenyl ring of the surfactant interacted like this way, or it may interact like this, like a pi-pi interaction, or the chain of the surfactant may interact like this. So we don't know, right? But if we use the quantum chemical models, again we can see the lowest energy conformation. Here you can see when there is something like a pi-pi interaction, we can see the lowest energy. That means when I perform the experiment, most probably the surfactant may present on the carbon surface in this manner. Now, one additional parameter we know if from the quantum mechanics, right? Because we are going more in a atomic scale to what is occurring, or to know about what is happening at the electrode interface. Then what we did, we used the HOMO-LUMO concept here. Here you can see LUMO orbitals of the this surfactant is known as benzethonium chloride. That's why it is benzethonium chloride modified carbon paste electrodes. So this is LUMO orbital. At the left side you can see. Okay, this is LUMO orbital of the benzethonium modified carbon paste electrode surface, and this is the HOMO orbital. LUMO means what is occurring here. I am seeing the dopamine electron transfer. That means from the HOMO orbital of the dopamine, the electron is jumping to here, right? It is nothing but oxidation of the dopamine occurs here. And here HOMO means the electron may jump from the benzethonium chloride to the dopohydroquinone. That means reduction of the dopamine. I'm talking in terms of the dopamine electron transfer. So this is the LUMO or home frontier LUMO HOMO or frontier molecular orbitals. Now we can see how to say Foucault function again here F minus and I think there is some, it should be F plus, F minus and F plus portion of the benzethonium chloride modified carbon based electrode. So both are matching, right? HOMO-LUMO and the mm, Foucault function. What it says, that means electron transfer process is mediating from the surfactants. In particular, the when surfactant phenyl ring and the surfactant phenyl ring mainly contributes for the electron transfer process. So then we made some experimental utility of this carbon interface. Here you can see we have detected the dopamine in presence of the ascorbic acid. At the bare carbon-based electrode, we are observing only one peak. That means for both dopamine and oxidation, dopamine and ascorbic oxidation, for both molecule oxidation, we are seeing only one peak. So we are not getting the real values, right? Because this peak may be due to the dopamine or due to the ascorbic acid. But in presence of the uh, surfactant, we can clearly see the peaks are distinguished. That means I can clearly know whether only dopamine is present or only ascorbic acid is present, or if both are present, I can know the exact concentration of both ascorbic acid and the dopamine. Then what we did, we have applied these electrode surface to see to know or to measure the dopamine concentration in the commercial injection samples. We got almost near to the 100% recovery results. So this electrode can be used commercially. Then we applied the same principle to to model the some another type of the surfactant, cetylpyridinum bromide. Again, here we have added surfactants at the different uh, concentration when we perform the experiments, and when we make the models, we have one time surfactant interacted with the by its chain, and that time that chain may be rotated 90 degree, or sometime head may be rotated. And this one here you can see like this, like a pi interaction. And we calculate, we this time we have also used the Boltzmann uh, uh, models, so to know like the effect of the temperature. Here we can see like D and E has the lowest energy, right? That means when we perform the experiments, surfactant may react like in this way. Maybe at this type of orientation, there may be the pi interaction may present. Now we have computed the Foucault function. Here you can see pyridinum, right? It's a cation, right? Therefore, it is easy, this cationic portion present here. Therefore, electron addition is feasible, but electron remotion is not that much visible because it is a cation, right? So here there is a less probability to receive the electron. Again, it matches with uh, experimental assumption, and Foucault results are matching. Then we used it to detect the uric acid in the human urine sample, and now how much we spiked, that much only we got the re- or that much uric acid only formed. That means if these type of the electrodes can be used to detect the uric acid in the human urine or the patient's urine samples, then when we perform this experiment, one of the reviewer asked us like, okay, you are doing two calculations. Once you have to calculate for the Foucault negative and Foucault positive. You can use the dual Foucault function so that you can uh, compute, or you can plot both electron donation and electron acception portion of the catalyst simultaneously. So I think we agreed with that point, and then we use the dual Foucault function parameter. Here you can see red color portion is maximum for the electron addition, and electron removal is from the blue color. This is matching with the, this is dual Foucault plot. This is matching with the normal Foucault plots. And then this time we went to use this electrode for detecting another molecule known as ascorbic acid. Again, here we are able to detect the ascorbic acid in the human urine samples. We got a relatively very good results. So at the end, what I want to say is like nowadays almost all lab have a cyclic Voltammeter potential stats. Even some basic undergraduate colleges also have this. And what is the use of this potential stat is you can develop a sensor and you can understand the electrode interface. In particular, if researchers start to use the academically free software, they can compute frontier molecular orbitals, Foucault function. In this way, they can start to, you know, interrelate electrochemical results with the quantum mechanics parameter. So these are very handy experiment. One can do it at a very low cost. So even a simple computer with the i5 processor also they can compute this kind of calculation, and these are economical. In this way, what one can understand when they perform the experiment, how catalyst may present at the electrode interface and how they mediate the electron transfer process. They can know it very easily. And to be very frank, these type of models and these type of interrelating electrochemistry and quantum mechanics has is very fruitful for our research. We have published couple of papers, uh, and we got very good collaborators also. Here we can see like we are collaborating with NUS, Tsinghua University, uh, University of Colima in an international level, and we are collaborating in a national level with GKVK Bangalore, Mangalore University, Shulini University. Within institutional also we are collaborating with certain researchers who are developing catalyst, and we are getting catalyst from them, and we are developing sensor and getting theoretical insights using density functional theory. So he is my postdoc research mentor, Professor Zhigang Shua. He teach me through him. I have learned density functional theory, and this is Professor B. K. Kumaraswamy. He is my master thesis mentor. From him I learned the voltammetric method. Here, Professor Roberto Flores Moreno, he's my PhD mentor. He taught me Foucault function, frontier molecular orbitals, density functional theory, Gimon 2K, synapses, all this software I learned from him. And he is Professor K. Mohanty. He is my research mentor for the SubTAR project, which was approved in 2022 by Government of India. We have completed that project also already. So our team is Miss Krutika. She is a PhD student. What she is doing, she is developing sensors for caffeic acid detection by nanoparticle modified carbon system. Another student is Surya Chetana. She is also developing some kind of the esters to or the binding materials for the graphite based electrodes for sensing caffeic acid. And recently we have one more addition, Mr. Vinay Kumar. He is working mainly on the molecular dynamics. We are now thinking to expand our model, like size of the model. That means we are even going for the molecular dynamics. That means Newtonian mechanics simulation. So we had several past members, particularly they done master's thesis with us. Miss Sinchana Kudur, Namrata Anaji, Mr. Navneet, and Miss Tanushree. They all worked on some kind of, they were more interested to detect the pesticides using carbon-based electrode system. So this, as I told, the combination of cyclic voltammetry and density functional theory helped us in a very good way, and it gave us some recognition for this for clubbing Foucault function and the voltammetry. First we I got the PhD award from the government of Mexico by the CONACYT fellowship, and then we got Subtar project from the government of India, and our sensor developing idea was liked by the Defense Ministry. They gave us a Day to Dream Award in 2022, and luckily these papers are cited very highly. As a result, we got the top 2% scientist award in 2023 and 24. So some of the local newspaper also covered our research. So we have also completed one project from the state government of Himachal Pradesh. Here, what we developed, like we developed the graphene and uh, you know uh, uh, biocompatible graphene. That means we take the two type of graphene. One is normal graphene, another is graphene modified from the amino acids to detect the how which can be helpful for drug delivery. That means using density functional theory, we were able to know how the amino acid modification of the graphene system useful for the drug delivery application of cisplatin and doxorubicin. And then we got one project from the Ministry of Electronics and Information Technology. This is a joint project with the Amazon Web Service and the MIT Government of India for developing quantum chemical models to understand the catalysis of lactic acid tailored graphene surface for sensing heavy metal ions. We got this one is the Subtar project with the IIT Guwahati collaboration. So here in this project also we have complete. The idea of this project is how to developing surfactant modified carbon electrode surface for detecting pollutants like linden and hexabromocyclododecane. So these are all the funders for our projects: DRDO, DST, Niteminakshi, Management, HIMCOST, Amazon Web Service, and MIT. All of them have helped us very much for getting fundings and to perform the experiments. And I'm very thankful to our management, uh, our administrator, Mr. Rohit Punja, for providing platform or space to perform these experiments at the Nitya Meenakshi Institute of Technology. And thank you.